Summer solstice. That's coming up 3 months from now, okay? That's going to be when the Earth is fully tilted, the northern hemisphere is fully tilted 23.5 degrees toward the sun, all right? And that's also very easy to figure out. You take your equinox solar altitude, which we already determined for Prescott, 90 minus our latitude, 35 degrees, equals 55 degrees. You simply add the 23.5 degrees as we're going to approach that full tilt 3 months from now. So we're going to add 23.5 degrees to get the solar altitude for our summer equinox, or summer solstice. For winter solstice, we simply take the equinox solar altitude and subtract that 23.5 degree tilt. So let's do that for Prescott. Let's run the numbers here, all right? So remember how equinox solar altitude, 90 minus your latitude, we're at 55. We take the sine of 0.82, we get 82%. So on both equinoxes, we're going to get one today, and we're going to get one 6 months from now in September, around September 20th. But now, if we do, this is going to be our summer solstice. We're going to take that 55 degrees, we're going to add the 23.5 degrees, we're going to get 78.5 degrees. What does that mean? That means on June 21st, you guys, here in Prescott, when we measure solar altitude, that sun is going to be at 78.5 degrees, much higher in the sky than it's going to be today. It's going to be 23.5 degrees higher on June 21st. So if we run the numbers on this, the sine of 78.5 is 0.98 multiplied by the 100%, 98%. So in the summertime, June 21st anyway, when that sun's up at 78.5 degrees, you guys are getting 98% of the total possible solar intensity. That's a lot. So you get a pretty high sun here. Even though it's never directly overhead here in Prescott, that is pretty high, 78.5 degrees. Now, let's run the numbers for the winter solstice. Our equinox solar altitude, 55 degrees, subtract the tilt of the Earth, 23.5. We come up with 31.5. So look at the difference. Look at the difference between these two numbers here. And the difference is always going to be 47 degrees. If you subtract 47 from that, you get 31.5. That's because over the course of 6 months, when we go from being tilted 23.5 degrees away to 23.5 degrees toward, what you're going to see in the sky is the sun move a full 47 degrees higher, and then after June 21st, it's going to move back down 47 degrees over the next 6 months. Now, let's run the numbers on this zone. This becomes kind of interesting. The sine of 31.5 is 0.52. So if we multiply that by 100%, we get 52%. This slide explains right now why there's winter and summer in Prescott. Look at this. Summertime, solar intensity almost twice what it is in the wintertime, okay? The point to take from this is that in the summertime then, much more solar intensity is going to heat the land surface up a great deal more. That land surface is then going to heat the air above it. In the wintertime, not so much. Okay, like I say, almost half the solar intensity. So the ground will not get as warm. That's why the air is not as warm. So that's why we have it. You know, that's why we have seasons here in Prescott. It's simply based on the differences in solar intensity. Okay. Let's take a look at this. How do we measure air temperature? We have strict protocols for doing this. Okay, here's a diagram of it right here. First of all, we take measurements with thermometers inside a white box that allows air to go through it. These are called louvers here, so air can go through it. When we take, like for example, we said today the high temperature expected here is 68 degrees. That's in the shade. That's in a shaded box. It's not out in the sun. Okay, so louvered box, painted white, and then it also has to be precisely 1.5 meters above the ground. That's just about your eye level. Okay, so we don't want our thermometers right down on the ground. Like I say, about not about, but 1.5 meters above the ground. Also, the surface over which we put this box. By the way, this is called a Stevenson screen. Again, this is the type of equipment used all over the world. By the way, the Stevenson screen also has to be over ground that is natural. So in other words, you don't want to be putting this over blacktop, all right? An interesting occurrence happened about a year ago. For probably 80 years, the world record highest temperature was taken in Libya. If you look at that map of the of Earth up there, Libya, look the very northern coast of Africa and along the Mediterranean Sea. Libya's there. It's the middle country you're looking at there. A town in Libya had the world record temperature, 136 degrees Fahrenheit. Number 2, for the same number of years, about 80, was Death Valley in California. For whatever reason, the World Meteorological Organization, a branch of the United Nations, got concerned that this reading in Libya may not have been accurate. So they sent a team of 3 people from the United Nations over there about a year ago to inspect their station. First of all, they found their station over black asphalt. And what might be the problem with that? Yeah, black asphalt absorbs a great deal of shortwave solar radiation, heats up, heats the air above it. Okay, that's one strike against it. I won't even go into the details here, but let's suffice it to say there was very good evidence that the guy reading it that day made an erroneous reading. Another way they tried to correlate that, or they attempted to correlate that, was they looked at all the closest weather stations that day for its maximum temperature. Nobody was even close. Nobody was closer than 8 degrees Fahrenheit. In other words, 8 degrees lower than the 136. Anyway, these guys came back and made their presentation to the United Nations, and the United Nations struck the Libyan record. It's no longer the official world record. So guess who has the official world record now? We do. Death Valley, United States, is now bumped from number 2 to number 1. All right, now, let's get back to this. So we're measuring air temperature at 1.5 meters above the ground, about your eye level. It's about 5 feet. So why do we do that? Because what we find is that if you take the temperature right at the ground, if the sun's, say, up high in the sky, the ground temperature can be considerably higher than the air temperature. And it really depends what kind of ground you're on. Like if you're on black asphalt, it's going to be extremely hot down here. If you are over a white surface, it's not going to be nearly as hot. So it's variable. So we want a better mix. We want a better, more accurate, even temperature. So we take it up here. All right, let's take a look at an example here of what can happen during a sunny day. You can, if we took the temperature of the surface, you guys are going to do this next week. We're going to go out in the field here. We're going to collect data. And we're going to collect several different types of data. One particular type of data will be the temperature of the ground. We do that with infrared thermometers. I have several infrared thermometers. You point them at anything, hit the trigger, and it will give you the temperature of the surface of anything you point it at. You could point it at that door, at the wall, at the ceiling, at the floor, anything. Give you an instantaneous surface temperature reading. So we'll do that at the surface. Now in this example up here, it's showing you a surface temperature of about 125 degrees Fahrenheit. Okay? But our thermometer inside our shaded louvered box is only reading about 95. So it's showing you a 35 degree temperature drop just 1.5 meters above the ground. Now, the main reason for that is the ground, a solid, is very good at conducting heat. So it can heat up quite a bit. But air is not. We need convection to heat the air up. And you can see that it doesn't transfer the heat very well at all just above the surface. So the surface can be very hot, but even 1.5 meters above the ground, quite a bit cooler. So anyway, that's what we call a microclimate. The temperature just 1.5 meters away can be much higher or lower than it is up here. Okay, so that's a daytime phenomenon.